Today I'm presenting post-quantum TLS without handshake signatures, which is joint work with Peter Swabe from the Radboud University, as well as the MPI Institute in Bochum, and with Douglas Stabila, who is at the University of Waterloo in Canada. And today we're going to be talking about TLS, so let's start with how did TLS 1.3 look like again. So TLS is a authenticated key exchange protocol. This is the scenario where we have only a server to client authentication and no client to server authentication. And there you can see that at the start there is a Diffie-Hellman key exchange from which a key is derived that is used to send over a certificate. And then there is here a signature using the public key in that certificate that is used to authenticate the server to the client. Now, how do you make this post-quantum? Well, you just write post-quantum signature instead of a pre-quantum signature. And instead of the Diffie-Hellman key exchange, we could use a post-quantum KEM. So that seems like this is more or less straightforward. You put post-quantum KEMs in your key exchange. Well, that's been done. There's a few papers about that. You can use post-quantum signature in your authentication. There's also a paper that looks at that. And all of these papers also evaluate the performance of doing this. And the security is similar to the proofs that you have for TLS 1.3, just now with post-quantum primitives instead of the classically secured primitives. So we're done, right? Well, that's the thing with post-quantum signatures. They are quite a bit bigger than KEMs in terms of that the sizes of the signatures and their public keys combined are often quite a bit bigger than the sizes of KEM public keys and KEM ciphertexts. They are often quite a bit slower than KEMs to compute, and they use quite a bit of extra code because you can't reuse as much as you could before. So we're going to use KEMs for authentication instead. So what is a KEM? A KEM is a set of primitives where you can generate a key, use that to encapsulate to a public key of someone else. That gives you a shared secret, which is the secret you're going to establish with that other party, and a ciphertext. And you send that ciphertext to the other party, which allows them to obtain the shared secret if they also have the secret key that corresponds to the public key. So, for example, and we can use this to construct authentication protocols. So if you want to authenticate Douglas to Peter, we can start with that Peter sends over a ciphertext that is encapsulated to the public key of Douglas. Douglas can decapsulate that ciphertext using a secret key, obtains the same shared secret, and then through this sending over this MAC, we can Douglas proves to Peter that he could indeed compute this shared secret, and that he has thus proven that he has possession of the secret key and has thus authenticated himself to Peter. But this doesn't just work if we want to plug this into TLS. In TLS, the client does not already have the public key of the server. So Peter could, in the previous example, immediately send over the ciphertext to the server in the first message. But that is not possible in TLS because you can connect to any server in the world. And you don't have all of those public keys. So if you want to put this in TLS, you need to have an extra round trip. You would first need to say hi to the server, and the server needs to send over the public key. And if you do that naively, you need an extra round trip than the protocol we showed before. And one of the things that the TLS 1.3 working group tried very, very, very hard to do to get this handshake done in a single round trip. So they won't be too happy if moving to post-quantum means an extra round trip. But we can solve this. We use implicitly authenticated key exchange instead. the client encapsulates a secret to the server's long-term public key, but they do not wait until they get the MAC back before they start sending encrypting data under that key. This has been seen before in protocols such as HMQV, these CAM protocols, notably FSXY, but also in practical protocols like Signal, Noise, and WireGuard. So how does this work in TLS? We propose CAM TLS, which handles this protocol in two phases. So there's first the ephemeral key exchange, which more or less just plugs into what you were previously doing in TLS 1.3. We generate an ephemeral CAM key. The server encapsulates to that key, and the shared secret is used to derive a first encryption key to send over the certificate. Then in the second phase, the authentication, the server, the client encapsulates to the server's static public key that is embedded in the certificate and sends over ciphertext, which the server uses to compute the static shared secret. And then we combine these two keys, the ephemeral shared secret and the static shared secret, to compute a shared secret that the client immediately uses to start sending data to the server. So this preserves the ability of the client to send over a request to the server on the application layer in the first message. And the server then replies, and then after, with the key confirmation of its own, this authenticates the server to the client explicitly, and then we can also send application data from the server to the client. So you need to choose some algorithms to put in all of these phases. There is the ephemeral key exchange, for which you need a CAM with a small public key and a ciphertext. Surprisingly, this cannot be in CPA secure CAM. You need slightly more. You need to be able to answer a single decapsulation query if you want to simulate this. The server authentication CAM needs to be in CCA secure, which is also what you would expect. But here again, we want something that is fast in terms of computation time and also has a small public key and ciphertext, so you have fewer bytes on the wire. Then we have a root certificate. And this is actually an interesting thing because that root certificate is already present on the client. That is the anchor of the authentication path. So the client needs to already have that. This implies that we only care about the size of a signature made with that algorithm. This has some interesting consequences if you are looking at what types of primitives you would pick, that some characteristics turn out to not matter in certain applications, like public key size. And then there is the intermediate CA certificate, which is sometimes used to, or most of the time used in TLS. The root certificate is present on the computer, but then they use the root certificate to sign a intermediate CA certificate, which then signs the leaf certificates for all of the clients. And we will investigate CAM TLS with both with and without these intermediate certificates. So we're going to look at some scenarios in our experiments, because we also did experiments. We are going to try to pick algorithms such that we minimize the size when you transmit such an intermediate certificate or when you leave it out. For example, it was cached or you don't have one. And we'll see that we have different choices in algorithms there. Then we use one that is solely based on n-true assumptions, and one that's solely based on module LWE and MSIS assumptions. This gives us the following parameter choice. So you see that if you minimize size, you end up with psych and Falcon for handshake authentication, or you indeed use psych again. You see that if you want the smallest signature size, you end up with GEMS, which is our CA certificate here. And if you don't send over the intermediate CA, you also end up with GEMS. And in scenario 1, we use a custom version of XMSS, which is smaller, to also further minimize the signature size. And then scenarios 3 and 4 are basically n-true and Falcon, or Kyber and the lithium. And these are abbreviated as such. That was what the underlines were for. And you'll see these abbreviations come back later. So we did experiments, and this gives us some results. We implemented ChemTLS in Russells and also compared this to a post-quantum instantiation of TLS 1.3. And you can see here in the lower left corner the combination of RSA and X25519. So elliptic curve, RSA, RSA, RSA. You can see that it performs roughly equally than to N-true Falcon combinations and to Kyber dilithium combinations, although the variants where you have Falcon as a handshake signature authentication scheme or dilithium as a handshake signature authentication scheme are quite a bit slower. Not slower, they are quite a bit bigger. The difference in N-true and Falcon is not so pronounced, but Kyber and dilithium, you have quite a bit of savings. What's also interesting and not represented by this graph is that the difference in computation time between N-true and Falcon is a factor 10 or a factor 4 for Kyber and dilithium. So you save quite a few CPU cycles on the server side here as well. If you only need to encapsulate instead of producing a signature, saves quite a bit of time. Another interesting example is the Psych and Falcon case. This is the only case where using a handshake signature actually speeds up things, and that's because Falcon is quite a bit faster than Psych. So the choice of algorithm here clearly matters. We also have this example where you leave out this intermediate CA certificate, and then you see basically that you just save some size for the you also save some time. No, you don't save time at the server side because it's only sending over more data or less data. But the example where you have Psych and Falcon and GEMS, you see that because it doesn't need to send over quite a few bytes, it goes to the left and down a slight bit. So we see here that the size optimized variant of ChemTLS requires less than half the communication that the size optimized version of post-quantum signed key exchange uses. But a speed optimized version uses 90% fewer CPU cycles and still reduces the communication that you need. We need no extra round trips before the client starts sending application data. And we also have a smaller trusted code base because you don't need to generate signatures anymore in the server. You could, for example, use non-side channel protected code there to because you only need to verify a signature. Because this is a virtual presentation and not a talk, I'll try to answer a few of the previously encountered frequently asked questions. What about client authentication? Well, we provide a sketch in Appendix D, mostly leave it for future work, but the naive way unfortunately does require a full initial round trip, but that is no different from TLS, state of the art. People often ask us about TLS 1.30 RTT, so the ability to send over a data in the first request, but that is a resumption mechanism. And it is orthogonal to the things we're doing here in ChemTLS, and you could even do the same things. We also see some opportunities to have more efficient handshakes when resuming. The server in TLS 1.3 can, after it's sent over the server certificate verify message and its server finish message, immediately send over application data. And it's been used by, for example, HTTP 3, where the server sends over a settings frame. We only allow the server to reply after it's received the client finished message. This means that the server can only reply after 2 round trips instead of after 1. So this is a bit of a downside, but we argue that interesting data from the server to the client will often only come after the client has indicated what they need. Static information such as a settings frame could be solved in an extension to TLS, for example, a server-side variant of the ALPN extension that indicates from the client to the server what kind of protocol it wants to speak later. Another remaining interesting area of discussion is what you do about certificate lifecycle management. So issuing and revoking keys in certificates. So at first glance, many of these things seem very much non-trivial. For example, the revocation mechanism assumes that you can sign a revocation statement with the public key in your certificate. You need to really figure out something else there for ChemTLS, and this is also a good direction for future work. This gives an overview of our paper, Post-Quantum TLS without handshake signatures. We do implicit authentication via chems instead of explicit authentication via a signature, while preserving the client's ability to do a request after this single round trip. And we both save bytes on the wire and quite a few CPU cycles on the server side. This paper was recently accepted at ACM-CCS and should appear at that identifier at some point in the future, but you can find the full version with proofs today at this ePrint link. And we make our data sets and our experimental implementation public, and you can find all of that in the GitHub repository link below. Thank you for your attention.